Does light have weight? And is it actually matter? Back in the 17th century, Sir Isaac Newton suggested that light was made up of particles, which he called corpuscles. But this view was challenged as it couldn't explain certain behaviors of light, like diffraction. Fast forward to the 19th century, where experiments by Thomas Young showed us that light also behaves like a wave. You see, when light passes through a narrow slit, it creates a pattern of light and dark bands, showcasing its wave-like nature. Now, let's talk about photons. Photons are these tiny packets of light energy, which intriguingly have zero rest mass. That means if we measure just their mass, light wouldn't weigh anything. But here's where it gets interesting. Thanks to Albert Einstein, we know from his equation E=mc2 that energy and mass are two sides of the same coin. Photons might not have mass, but they do carry energy. And in the realm of physics, energy contributes to mass. This is what we call relativistic mass, the mass an object seems to have when it's moving. When light interacts with gravity, like near a black hole, it behaves as though it has mass, bending around the massive object due to gravitational forces. This phenomenon, known as gravitational lensing, is a stunning demonstration of light's effective mass in action. So, while light doesn't have rest mass, its energy means it isn't completely weightless either. When you look up at the stars, the light that travels across the cosmos to reach us carries with it this subtle cosmic weight, a testament to the profound interconnections of energy, mass, and the fabric of space-time. Isn't that something?
The speed of light is a fundamental constant of nature that plays a crucial role in our understanding of the universe. Let's explore it in detail. In a vacuum, meaning no material medium, the speed of light is precisely 299,792,458 meters per second. To put it in other units, that's approximately 300,000 kilometers per second, roughly 186,000 miles per second, or about 671 million miles per hour. Why is the speed of light important? First, it serves as the upper limit for information travel. According to the special theory of relativity, the speed of light, denoted as c, is the fastest that any form of matter, energy, or information can travel through space. All forms of electromagnetic radiation, including visible light, propagate at this speed. For practical purposes, light appears to travel instantaneously over short distances, but its finite speed becomes noticeable over long distances or in sensitive measurements. Second, observing starlight on Earth means we're actually seeing light from the distant past. This allows us to study the history of the universe by examining objects that emitted light billions of years ago. For instance, the light from the nearest star, other than the Sun, takes about 4.2 years to reach us. Third, in space communication, the speed of light sets the ultimate minimum communication delay. When communicating with distant space probes, such as those exploring other planets, signals take minutes to hours to travel to and from Earth. Finally, precision measurements. Scientists use the speed of light in time-of-flight measurements to determine large distances with extreme precision. Historically, in 1676, Ole Romer demonstrated that light does not travel instantaneously by studying the apparent motion of Jupiter's moon Io. In 1865, James Clerk Maxwell proposed that light was an electromagnetic wave and traveled at speed c. In 1905, Albert Einstein postulated that the speed of light is constant with respect to any inertial frame of reference, independent of the motion of the light source. His work led to the theory of relativity. Understanding the speed of light is crucial for comprehending the vast distances and the intricate dance of cosmic phenomena that shape our universe. Light, the captivating phenomenon that permeates our universe, exhibits a dual nature. It behaves both as a wave and as a particle. Let's explore this intriguing duality. Wave behavior of light. Light exhibits wave-like properties similar to other types of waves, such as sound waves or water waves. When we consider light as a wave, it undergoes reflection, bouncing off surfaces just like any other wave. It refracts, changes direction, when passing from one medium to another, such as from air to water. It can also diffract, spreading out when encountering small openings or obstacles. These behaviors are characteristic of waves and are challenging to explain solely from a particle perspective. Particle behavior of light, photons. Light can also be thought of as consisting of tiny packets of energy called photons. Key points about photons include energy carriers. Photons carry a fixed amount of energy but have no mass. Wavelength dependence. The energy of a photon depends on its wavelength. Longer wavelength photons, such as red light, have less energy, while shorter wavelength photons, such as blue or ultraviolet light, have more energy. Wave-particle duality. The concept of light behaving as both a wave and a particle is known as wave-particle duality. This duality is a fundamental aspect of quantum mechanics and challenges our classical intuition. Experiments, such as the famous double-slit experiment, demonstrate that light can exhibit interference patterns, typical of waves even when individual photons are involved. Double-slit experiment. In the double-slit experiment, light passes through two closely spaced slits. The resulting pattern on a screen behind the slits shows alternating bright and dark regions due to interference. Even when photons are sent through one at a time, they still create an interference pattern, suggesting their wave-like behavior. In summary, light's dual nature, simultaneously wave-like and particle-like, remains one of the most captivating aspects of physics. Whether we view it as a stream of photons or as undulating waves, light continues to illuminate our understanding of the universe. Let's explore the fascinating connection between the speed of light and time travel. If a person were to travel at the speed of light, they would experience a phenomenon known as time dilation. This means that time would move slower for them than for someone who is not moving. The concept of time dilation arises from Einstein's theory of relativity, which links time and space together. Albert Einstein proposed that our universe has a speed limit. Nothing can travel faster than the speed of light, approximately 186,000 miles per second. According to the special theory of relativity, as an object approaches the speed of light, its relative time, compared to a stationary observer, slows down. This effect becomes more pronounced as the object's velocity approaches, c. Achieving light speed is considered crucial for time travel because higher speeds lead to greater efficiency in time travel. The fastest speed we can theoretically achieve is the speed of light itself. When traveling close to the speed of light, time passes more slowly for the moving observer. If you were to embark on a journey at near light speed and return to Earth, you might find that less time has passed for you than for those who remained on Earth. This effect has been experimentally verified using high-speed particles and atomic clocks on fast-moving satellites. In summary, the speed of light not only sets a universal speed limit but also influences the fabric of time itself. While we haven't built time machines yet, understanding these principles brings us closer to unraveling the mysteries of time travel. Light, the fascinating phenomenon that illuminates our world, possesses a rich set of properties. Let's explore them in detail. Electromagnetic radiation. Light is a form of electromagnetic radiation that can be detected by the human eye. It spans an extensive range of wavelengths, from gamma rays with wavelengths less than about 1 × 10 circumflex, -11 meters, to radio waves measured in meters. The visible spectrum, which humans perceive as light, occupies a narrow band from approximately 400 nanometers, violet, to 700 nanometers, red. Speed of light. In a vacuum, the speed of light is a fundamental constant, precisely 299,792,458 meters per second, or about 186,282 miles per second. This speed limit shapes our understanding of the universe and plays a crucial role in phenomena like time dilation, perception, and communication. Through our sense of sight, light becomes a primary tool for perceiving the world and communicating within it. Sunlight warms the earth, drives global weather patterns, and initiates photosynthesis, the life-sustaining process. Exploring the universe. Light provides a window into the universe, from cosmological to atomic scales. Astronomers interpret electromagnetic radiation to glimpse the earliest epochs of the universe, measure its expansion, and study stars and interstellar matter. Interactions with matter. Light interacts with matter through phenomena like reflection, refraction, dispersion, and diffraction. These interactions shape everything from rainbows to the colors we perceive daily.